Hello, welcome to this webinar on best practices for using a water purification system. My name is Estelle Richer, and I'm Senior Scientist in the Training and Application Group of the Labwater business field of Merck Millipore. You may have a water purification system in your lab, and you may be wondering about the best way to use it. So in the next few minutes, I will give you some tips about the best way to handle both your water purification system and the high-quality water that it delivers. So the reason why we are talking about water today is because water is used in many different places in the laboratory. It is a very common reagent, and it is also probably the most abundant reagent you may use in your lab. It may be used to prepare reagents and standards, to prepare buffers and mobile phases for chromatography. It is often used as blank or in sample preparation for dilution, rinsing, or extraction. It may also be used for washing and rinsing containers. And this is something to always remember. Please take care of your containers and glassware by using high purity water for the last rinse. It will prevent any risk of contamination of your glassware. We will talk about this further on in the presentation. So what's really important for the water you use in your laboratory is that it needs to be free of any contamination that may compromise your results. And in the remainder of the presentation, I will explain to you how you can do this and get the best results. Okay, so first of all, we may think about what is in water, what other molecules are in water aside from H2O. So if you turn on your tap water, what comes out of it is, of course, mostly H2O molecules, but as well other contaminants. The contaminants are usually grouped into 5 main families. First of all, you may have some ions in your water that come from the soil it was in contact with. There may be some minerals like calcium, magnesium, also some chlorine, for example, and many other ions. Your water may also contain some organic molecules that come from nature. As leaves and pieces of wood degrade into water, they release some organic molecules. There may also be some very small amounts of other contaminants that come from human activities, such as pesticides or maybe plasticizers or even medications might be present now in tap water in very, very small amounts. So it is not bad for your health. However, it may have an impact on your experiments in the lab. Other contaminants that may be present in water are particles that come from maybe grains of sand or just very, very small pieces of objects that were in contact with natural water. There may also be some bacteria in your tap water. So, of course, there are no harmful bacteria because those are treated with chlorine and other compounds like this. However, there may be some harmless bacteria since bacteria are everywhere in our environment anyway. And finally, there may be a few dissolved gases in your water. All right, so this is the reason why water needs to be purified before you use it in your laboratory, because it may contain some contaminants that will have an impact on your experiments. So usually, water purification is performed in 2 steps. The first step is called the pretreatment, and it goes from tap water to what we usually call pure water. And then the second step is called the polishing step, and this is what will give you really, really high quality water, which is also called ultra pure water. Water purification is usually done by combining different technologies in order to be sure to remove all the different types of contaminants that are present in water. Usually in the first step, in the pretreatment step, what is used is reverse osmosis. Reverse osmosis is a technology based on a porous membrane through which we apply pressure. So only water molecules will go through and other molecules will be retained on the other side of the membrane. So this technology is really efficient at removing a wide variety of contaminants. As you can see below, it can remove ions, organics, particles, and bacteria. However, it will not remove 100% of them, but depending on the type of contaminant, it may remove between 95 to even 99% of those contaminants. So this is really efficient. It's a very good first step. However, this technology is very sensitive to particulates and to chlorine. This is the reason why we have a pretreatment cartridge to protect it. Then the next technology that is very often used in purification system is called electrodeionization. So this technology is just a more advanced technology than simple ion exchange, but it serves the same purpose, so it removes ions. It is very efficient at removing ions, but it will not do anything else than that. The following technology you can see is UV light. So UV at 254 nanometers is used in order to keep bacteria under control. This will actually have an effect on the DNA of bacteria and kill them, or at least suppress them. So now I've described the technologies for the pretreatment. Now, if you need water that is of really, really high quality in order to perform experiments such as HPLC, ICP-MS, this type of very, very sensitive analyses, then you will use a polishing system, like, for example, the Milicu system. This system will combine, once again, some UV light, but this is UV at a different wavelength, which will actually photo-oxidize organic molecules and break them down into small pieces. It also uses a combination of ion exchange resin, which will remove ions, as its name suggests, as well as activated carbon, which is really efficient at removing organic molecules. So overall, the combination of all those technologies will give you water that is of extremely high quality. Then the last step is usually a filter, a 0.22 micron filter, in order to remove whatever is left of bacteria and particulates. So now that I've explained to you what types of contaminants are removed from your water in order to generate water for your lab, I will talk to you a little bit about how you can optimize the quality of water that comes out of your water purification system, because using a system is a very good first step, but it is not the only step that you should take into account. So the first advice I would have for you is to really perform regular preventative maintenance. This is the same as you would do for your car. It's always better to do regular maintenance instead of waiting for it to break down. This is the same for your water purification system. So please be sure to replace your cartridges and your filters on a regular basis, as it explained in your manual. And also, when new cartridges are installed, please be sure to rinse them a little bit at the beginning, just to be sure they give you the optimal level of water purity. So just as an example of the impact of not changing filters on time, for example, this is about the final filter, the 0.2 micron filter that is usually placed at the very end of a water purification system. What is shown here is a UHPLC chromatogram. So the red line is what happens when older filter is kept on the system. And as you can see here, there is an unknown peak that appears at about 3 minutes on the UPLC. However, if the same user changes his final filter and uses a new one, then the baseline becomes of much higher quality. So really it's important to be sure to change filters and packs on time. Another advice I would like to give you is to monitor the quality of the water you obtain from your water purification system. So most systems will display some values like this one, and I will explain to you quickly what these numbers really mean. So first of all, one important contaminant to monitor in water are ions. And the way we monitor ions in water is by simply looking at electrical conductivity, because extremely pure water without any ions in it will really not conduct electricity very well. And the more ions are present in water, the more it will conduct electricity. So really conductivity is a very easy and meaningful way of looking at ion contamination of water. So if water is extremely pure, the theoretical value of conductivity of that water will be 0.055 microsiemens per centimeter at 25 degrees Celsius. And since this value is not so easy maybe to talk about, usually people report the resistivity. Resistivity is the reciprocal of conductivity, and in this case, if you have extremely high quality water, its resistivity will be 18.2 megohm centimeter at 25 degrees Celsius. And I am sure if you have a good quality water purification system in your laboratory, you have seen this magic number of 18.2 being displayed on the instrument. This reflects the purity as far as ions are concerned. So as we have described earlier, ions are not the only important contaminants in water. Other contaminants to worry about are organics, because organics may have an impact on your experiments. So it is very important to also monitor the level of organics in your water. And this is done by measuring what is called the TOC, which is the total oxidizable carbon. This really represents the total amount of organic substances that are in the water. And it is usually expressed in parts per billion, which means micrograms per liter. And it is measured by simply oxidizing and then detecting the result of the oxidation. Those two values, the TOC value and the resistivity value, are both extremely important to reflect the quality of the water you will be using for your experiments. It is important, however, to remember that resistivity and TOC values have no correlation. So just because your system displays a resistivity of 18.2 megohm centimeter does not mean that your water is extremely pure. It may contain a lot of organics, but you may not even see that organics are present because resistivity only looks at ions. So this is just a small experiment we did to express this. All we did is we added some sugar to the reservoir, and then that water was passed through a polishing system. So after a while, the polishing system was overwhelmed by the huge amount of sugar present in the water. And so what you can see here is that in blue, the resistivity remains the same. There are very few ions in that water. It's really good. However, the TOC goes up drastically over 1,000 ppb. This is really to show you that 18.2 megohm centimeter is only part of the indication you need to know whether your water is good or not. Another good practice with water purification systems is to flush the system before collecting water. This is really true if the system has been idling. So for example, when you arrive on Monday morning, if the system has not been used in the weekend, I would recommend you to discard a little bit of water before you start collecting water for your experiments. So these two graphs are just to show you what happens on HPLC, for example. If you take water right away, so the pink lines are after just 100 milliliters of water being disposed of. And then as you can see, when 1 liter has been discarded in yellow, then it's a little bit better. But then when 5 liters have been discarded, that's the green line, you can see that both in HPLC or in LCMS, the baselines are of much higher quality. So don't hesitate to discard a few liters of water. This is done very quickly. It takes just a minute or two, and this will really greatly improve your results. Another case where it's important to flush water from your system before collecting water is if you're worried about bacteria contamination. So most systems have a filter at the end, at the point of use. This filter is a 0.22 Micron filter that is designed to retain particulates and bacteria. However, as you can see here, if water is collected right away, there are a few bacteria present. Depending on the day, it may vary between 5 and 86 CFUs per ml. And if, however, you discard a little bit of water, then you will not see any bacteria coming out of the system and of the filter. So what this indicates is that the bacteria actually came from the ambient air and penetrated into the outside part of the membrane. So it's really important to flush out those bacteria that come from the air in order to have really clean water without bacteria. So once again, a few liters, so that will take a minute or two, and that's perfect. You will have high-quality water. Another good practice is really to use freshly purified water and try not to store highly pure water. Because unfortunately, high purity water is an excellent solvent and it will not stay highly pure for a very long time. Since it is extremely pure, it will tend to try to grab contamination from its environment. So whether it is from the air of the lab or from the container it is placed in, it will tend to degrade. So if at all possible, try to use really freshly purified water. So to illustrate the potential for the air of the lab to contaminate your ultra-pure water, you may notice that your water is contaminated with ammonia, which is very present in laboratory air. And another thing that will happen is that CO2 will contaminate high purity water by dissolving into it and generating bicarbonate and carbonate, which will increase the conductivity of the water or decrease its resistivity. The air of your laboratory does not only contain ions that may contaminate ultra-pure water, but it probably also contains organics that may contaminate water as well. Those may come from organic solvents that are used in the lab. So this experiment is to show this. So this is electron spray ionization, mass spec. And what you can see here is that the freshly purified water on the left has a very low level of organic contamination. However, after 2 months of keeping water in a bottle and just opening it in the air about 3 times per week for 15 minutes, then the level of organic contamination is much higher. So usually the recommendation I would have if you do organic analysis, HPLC, UHPLC, or LCMS, I would recommend you use freshly purified water every day. So every morning discard whatever is left of the water from the day before and get freshly purified water. That way you can really be sure your results will be the best. So just to show you the effect that storage may have on HPLC, not only does water get contaminated from the air of the lab, but it can also be contaminated from the container it is placed in. One thing that is really not very good when you do organic analysis is to use plastic to store ultra-pure water. What you can see here is these are baselines obtained from water that was stored in plastic for a few days. And really, even just on the first day, it's not good to have water in plastic. What happens is plasticizers are released from the container into the ultra-pure water, and then you will see those on your chromatogram. So really, it is important to avoid plastic at all costs if you do organic analysis. Now, if you do ion analysis, then issues can happen as well. In addition to having contamination from the air, potentially, you may also have, of course, contamination from the container if it contains some ions. Another thing to worry about is try not to keep standards for too long. So this was just a small experiment that was done where standards were prepared in the evening and ran right away, and then kept overnight in an autosampler and ran again. And what you can see here is that the levels of both the sodium and the magnesium have increased overnight. So we don't know exactly where that contamination comes from. Is it from the headspace in the vial or is it from the vial itself? We're not sure. But in any case, it really shows you that standards need to be prepared fresh in order to get the best results. Another good practice is to really be sure to select the proper container for your analysis. So it is quite common knowledge that it is better to use plastic containers if you do ion or elemental analysis, and it is also better to use glass containers if you do organic analysis. In all cases, your containers should be really carefully washed and rinsed. In our research laboratories here at Micron, we really try, in many cases, not even to use any detergent in the containers that we use, and use, for example, for elemental analysis, we use acid and then rinse a lot with high purity water. It is also not good to mix containers from one type of analysis to another because there is more of a risk for contamination. So all those are really common sense pieces of advice, but these are really quite important, especially if you perform trace analysis. So just as an illustration to show you that containers may actually contaminate your samples with organics, for example, here is a case where we used either polyethylene HDPE containers or PP containers, and we simply placed some really high-quality molecule water inside those containers and rinsed them for 24 hours and then discarded, and then added more water for another 24 hours, discarded again, and repeated this 3 times. What you can see here is that the level of TOC, so the level of organics present in that water, is quite high on the first time, and then as time goes on, then it goes down. So that means that the level of extractables is very high at the beginning. As time goes by, as the volume of molecule water in contact with those containers increases, then the amount of extractables goes down. So this is one of the cases where it may be better actually to use older containers than to use new ones, because the older ones will have been very well rinsed and will no longer have extractables that may go into your sample. For those of you who work with ions or elemental analysis, the issue is quite similar, and even if you use really high quality containers, it's really important to rinse them really well. And depending on the level of your analysis, if you may still see some contamination. No matter what you do, you may still see low levels of contamination. This is, for example, data from ICP-MS experiments, where you can see that both PFA and PVC will release some elements, even though PFA seems better for some contaminants or PVC better for others. So depending on the type of ions you analyze, you need to really select the proper container for your experiment. So another piece of advice I would have for the use of your water purification system is to really try to avoid using plastic tubing at the outlet of your system, because this plastic tubing will really bring some contamination into your water. So basically what happens here is that the water delivered by the purification system is of really high quality, and then when it gets in contact with the plastic, it will either get some plasticizers from the plastic, or even bacteria or algae may develop in the plastic tubing. So at the end, the water you will collect after this piece of tubing will be of much lower quality. So this is really a very simple but very important piece of advice. Another quite simple and straightforward piece of advice is to try not to collect water straight down into a container, because this will generate bubbles, and those bubbles may bring in contamination into your sample. They will bring air from the lab, and this air, as we've discussed earlier, may contain some ions that will contaminate your sample. So I would recommend to tilt a little bit the bottle or the container you use to collect water, whether it is to prepare your samples or to prepare eluent, for example, for chromatography, in order to avoid forming any bubbles in your container. Another good practice is to try to minimize the use of wash bottles. I know wash bottles are extremely convenient in a laboratory, but the problem is, even if water is of really high quality at the time when you put it in the bottle, after a little while, you can be sure that the quality of the water will degrade quite a bit. And then you will not know what you are using to rinse with your wash bottle. And you may actually really introduce some contamination by using those bottles. The plastic of the bottle itself may contaminate the water, but also the air of the lab may contaminate it. So if there are some volatile organics in your lab, they will penetrate in the wash bottle. CO2, of course, will penetrate. Other ions will penetrate. So it's always best to use water that comes directly from the system instead of going through a wash bottle, as much as you can, of course. All right, and as I'm getting towards the end of my presentation, I wanted just to give you a few additional tips really quickly. So one thing is, it's important to keep your water purification system as well as the container you may use to store water, even though we said it's better not to store it, in a clean environment. If you're storing water in, for example, a washroom that's quite dirty, or near a hood that is being used with strong organics, or that is quite dirty, then you may contaminate your high purity water. So it's really important to look around and be sure to place it in the best location in your laboratory. Another small tip is, once you collect water from a system, try not to walk around in the lab with your open container, because it will increase the risk of contamination from the lab air. So if you can, then collect water in a bottle, in something you can close before you walk in the lab with it. Another thing is that not only solvents in the laboratory can contaminate water. Other things can contaminate it, such as cleaning products or glue or paint or furniture from your lab. If you're doing extremely sensitive trace analyses, make sure you watch out for those, really. Once again, think about your environment, because ultra-pure water is extremely, extremely sensitive to all those contaminants that might be present in the air. Finally, another thing to watch out for is the use of oil-based pens, Scotch tape or label tape, parafilm. All these types of products may release some contamination into the air and into your water as well. And finally, the source of contamination of your water may actually not come from water. It may actually come from something else. This is just an example of a case where the contamination actually did not come from the water, but came from the small amount of reagent that was added to water in order to prepare mobile phase for ion chromatography. So really here my advice is to, of course you know this, but to use really the highest purity reagent possible. And finally, one last piece of advice is to watch out for the filters you use to prepare your sample. You may have a really high quality sample, but if you don't use the proper type of filter, you may actually introduce quite a bit of contamination into your sample. So here you can see just an HPLC trace, and you can see additional peaks that appeared, and that came from using the wrong type of filter. But filters may also release ions in addition to organics, so this is really something to watch out for. So in conclusion, I hope I convinced you that water is not just water. Even though water is used everywhere in the laboratory and may feel like this is a very common solvent, it is really a reagent, and it should really be used in the same way as you would use other reagents, and you should take the same care with your water as you would take with other reagents in your laboratory. Another thing I hope you understood from my presentation today is that really having a good quality water purification system in your laboratory is a wonderful thing. However, it's only the first step. Once you have a good system, then you need to be sure you really use it in the correct way and that you maintain it properly so that you continue having the best water quality possible available for all your experiments. And finally, I give you today some good laboratory practice ideas in order to obtain really high purity water, and this will really be important for you to get the best results for your experiments and really boost your laboratory productivity. This is the end of my presentation. Thank you very much for your attention. Below you will find my email address. Don't hesitate to contact me if you have any question about this presentation. You may also visit our website at www.merckmelipore.com if you want more information about our water purification systems, the various technologies, and the various applications for them. Thank you very much.